Welcome back to Honors Calculus. In this video, we want to look at density and accumulation functions. So far in your mathematical career, whenever you have talked about functions, you've talked about things that you can work through as a graph. And you've talked about things where evaluating the function at a point can be used to solve problems. A density function technically can be used in that manner, but doing so is usually not helpful. You're familiar with the idea of density from physics. If you take the volume of an object and divide the mass of the object by that volume, you get the density, the mass at each point on the object. And I'm sure you can imagine an object which has some regions that are more dense and other regions that are less dense. And you could create a function that talks about the density at each point on the object. But what use is density besides translating between mass and volume? Evaluating the density at a particular point in an object whose density is changing doesn't really help any. The usefulness comes from adding together the density at every single point to get the total mass. And that's what we're talking about here. A density function can be used as a way of defining a function by integral. That final result is what we're talking about when we talk about an accumulation function. Let me get my head out of the way and let's dive right in. Right? An accumulation function is any function defined in the form capital F of x is the integral from x naught to x of f of t dt, where little f of x is the associated density function. Again, when you're thinking about this, think back to the Riemann sum definition of the integral and see if we can make sense of density in this context. The Riemann sum asks you to take a region, slice it up into a bunch of pieces, and add together the area of each of those pieces. If instead of calling the function a height and calling the space underneath the area, if we call the height of the function the mass or the density, then the height under the function is a little piece of mass. So we're taking an object that has a varying density, we're slicing it up into a bunch of tiny pieces. We're calculating the mass of each of those pieces individually. We're adding them all together to get the total mass of the object. Another place that density functions show up a lot is in the context of probability. We can think about the probability of scoring an exact time in a race. But for a race that works over an appreciable amount of time, and for a timing system that has an appreciable level of precision, there are effectively infinitely many different times that a person could finish at. And so effectively, the probability of finishing at any one of those times is zero. It's taking a range of times and adding together the probability of all of the times in that range, that gives you something appreciable, non-zero, and useful. So we take the density of probabilities and add them all together to get the probability of something happening within that range. All right, those are some of the ideas that hopefully will give you a little bit of a sense of what we're trying to do with this. But for our purposes, just being able to do it is good enough. I also want to look at the specific definition here because we've got a bunch of variables happening. First of all, instead of having x inside the integral, all of a sudden we have t. That seems a little bit strange. It is a little bit strange, but it is there because it works. Oftentimes you'll see the structure like this called a dummy variable. The only point of the variable that happens inside the integral is to figure out where your limits of integration are being applied. And since one of our limits of integration is already x, having x in here as well is going to make it confusing, right? X equals x naught and x equals x seem like contradictory statements. And so the notation of using some other variable in here makes it so that you can put x out here as a limit. All right, so the x out here is the variable for the function that we're working at. The accumulation function has an independent variable x. That independent variable is one of our limits of integration. The guy down here, x naught, is a constant. And it turns out that we can pick any constant we would like there, and changing that constant will change the x-intercepts of the accumulation function. The accumulation function evaluated at x naught will always have a value of 0. That's something that should make sense, and you should be able to think about geometrically. I'm not going to go into the details here. We're generally going to work with functions where our 0 is defined at x equals 0. It's going to make the math a little bit easier. There's a lot you can do with accumulation functions. For right now, our big purpose is to just give you some of the vocabulary. But it's also not unreasonable that we'll actually be able to evaluate these things. To see what I mean, let me get my head out of the way, and let's go into a specific example. Right, let's decide to define an accumulation function f of x as the integral from 0 to x of t squared dt. We know what the parabola looks like, and we know that this is calculating the area under the curve of a parabola. Right, to see a little bit better what I mean, let's jump over to Desmos. And you can see here that I've graphed in, what is that, orange, green? I don't know, I'm colorblind. But I've graphed the function f of x equals x squared. That's our density function. And then I have a slider here that is drawing the area underneath that density function and allows me to change the value. As I change the value of a, that's changing the upper limit, and I'm slowly growing this density function or slowly shrinking it if I'm going the other way. All right, as I add little bits more on, as I change the value of x, I'm accumulating more and more of the area. That's what we're talking about when we're talking about an accumulation function. Now, because we have so many unknowns, it's hard to do things graphically, so I am going to be forced to turn back to the Riemann sum. And in general, I'm looking at the limit as n goes to infinity of the sum, k goes from 1 to n of f of xk delta x. Now remember here, again, because x is one of my limits, talking about x in this case doesn't quite make sense, and that's why we switched to that dummy variable. So instead of xk and delta x, it's going to be tk and delta t. Just a change of variables so we're not using x to mean too many things. Remember that tk was our a, which in this case is 0, plus k times delta x, or in this case, delta t. And delta t was our bx minus our a, 0. X minus 0 is just x divided by n. And so we can substitute these things in to our summation. We're still taking the limit as n goes to infinity. We're still summing. K goes from 1 to n. But now we're evaluating f of k delta t times delta t. And I said I was going to substitute in the meaning of delta t. Let me go ahead and do that as well. Delta t is x over n. So k times x over n times x over n. Now, what is f? F is t squared. So I take the stuff inside there and I square it. So I still have the limit as n goes to infinity. I still have the sum. K goes from 1 to n. And then I take all the stuff in there and I square all of it. So it's going to be k squared x squared over n squared times x over n. Which is k squared x cubed over n cubed. Now here's where things get a little bit tricky. Because in my summation here, the only thing that I care about, the only thing that I'm treating as a variable in my summation is k. So this is a variable, and this is all constant. And constants can come outside of the summation. So I have the limit as big N goes to infinity of x cubed over n cubed times the sum, k goes from 1 to n of k squared. I know how to deal with that. K goes from 1 to n of k squared is one of those summations that we talked about a couple videos ago. So my x cubed over n cubed stay the same. The sum, k goes from 1 to n of k squared, is n times n plus 1 times 2n plus 1 all over 6. I'm going to leave the x cubed factored out, but I'm going to distribute all of that other stuff. In fact, while I'm talking about this, right now I'm looking at a limit. Use the right color in the right places. I'm talking about a limit on n. N is the only thing that I care about as a variable. X is a constant, so I can bring it outside of the limit. And that will make the algebra here a little bit easier to follow in general. So x cubed times the limit as n goes to infinity. Distributing in the numerator, I'm going to have n cubed. Let's see. N times 1, 2n times 1 is 3n, times n is going to be 3n squared. And then 1 times 1 is 1, times n is n. And here, finally, at this point, we're taking the limit of an algebraic function. We can go to our rules for limits of algebraic functions. We'll notice that this is going to be an infinity over infinity indeterminate form. And when we have an indeterminate form, we can divide numerator and denominator of the fraction by the highest power on n that appears. In this case, that's n cubed. The x cubed in front stays an x cubed in front. The limit stays a limit. But then we divide. N cubed divided by n cubed. I'm sorry, I lost something. N times 2n should have given me a 2n cubed. That's going to actually be important in a little bit, so I'm glad I caught that now. All right, but 2n cubed divided by n cubed is 2. 3n squared divided by n cubed is 3 over n, and n over n cubed is 1 over n squared. Now, when you evaluate the limit, this one goes to 0, this one goes to 0, and we're left with 2 over 6. Two over 6 reduces, and it's going to be 1/3 x cubed. Long way to go. It's not an easy process, but it's also not a particularly challenging process. It's a tedious process more than anything else. You have to go through a lot of algebra. You have to be careful. You have to pay attention to what you're doing. You have to hope that you know how to take care of the summation once you get to a summation. The important things here are, first of all, recognizing that the thing that we have can be rewritten as a summation. Second of all, recognizing which things are constant and which things are variable in terms of everything we're doing at every step of the process. Once we have those things established, we can factor out the constants, we can evaluate the summations using our summation rules, we can evaluate the limit using our limit rules, and we can simplify from there. All right. To wrap up, here's a very similar looking one for you to try. I would like you to figure out capital G of x given as the integral from 0 to x of 2t dt. All right, take a couple of minutes, see what you can do with that problem, and I'll see you in the next video.